So today's lecture content is Pausa double integral. So we will just continue our previous lecture on Pausa double integral. Okay, so let's just summarize our previous lecture. If we have to consider this MOSFET, so now we have a source and drain, and that is gated. In this case, we introduce a certain coordinate system. So y, which starts at 0 and ends at L, that is corresponding to the channel direction. And also we have another axis corresponding to the x and vertical direction. And it starts from, not exactly starts, but its interface starts at 0 and go to the deep substrate, so go to down up to positive infinity, and maybe we can find something called as a gate at x equal to minus t ox. Of course, this structure is really three-dimensional, so we have one missing coordinate, so corresponding to this g direction, x, y, z. However, along this g direction, we assume the homogeneity. So if we have one micrometer wide device, then maybe we will have just 1 micrometer. If we have 2 micrometer wide device, then yes, without any difficulty, so we can just extend it to in this way. So this W is really scalable. So if you wanted to have a high current drivability, then simple way is just to introduce a wider device. Then you will have much more current by spending the silicon area. So that's the reason why in this consideration we don't care much about this z-axis. So it becomes just a two-dimensional problem. However, still this two-dimensional problem is difficult to consider. Within this system, now we have to understand everywhere the potential as a function of a position x and y, and also we must consider the electron quadriform potential, which is a function of x and y. In order to solve these two quantities, actually we have to solve Poisson equation. However, Poisson equation is just one single equation, and we have two different unknown variables, so we need another one corresponding to electron transport. So that was a thing we have to consider. But anyway, both of these Poisson equation and electron transport equation, electron continuity equation, they are actually two-dimensional equations. So in this sense, we have to consider partial derivative with respect to x and also partial derivative with respect to y simultaneously. So this is not very convenient. So our previous lecture made a great simplification of this sense. So one was, okay, although we have to consider phi n as a function of x and y, but if x is nearby 0 interface or the most important position, then we can say that regardless the value of x, this electron quadriform potential share the same value. So instead of considering this phi n as a function of two-dimensional space, we just introduce a single variable quantity, so dependent on single variable v of y, so only channel position dependent. It means that if we have a certain position y, then nearby this y position along this x-axis, they share the same electron quasi Fermi potential. Also, we say that if we just change the value of y, then we will have a different value of v, but they are all shared by this vertical direction. So basic argument for this assumption was our electron current density is actually a vector field, and it can have x directional component and y directional component. However, this x directional component is vertical directional current conduction, and from the structure of this MOS system, current is allowed it only along y direction, not along this x direction. So we should not allow this kind of thing. So simply speaking, phi n, when we project it onto this x directional unit vector, then it should almost close to 0 to prevent current conduction. So that was our argument to introduce this y dependent electron quasi-Fermi potential. And also that was one thing, and another thing was gradual channel approximation. When we consider Poisson equation in its original form, of course we have to consider this x directional second derivative and also y directional second derivative. However, this y directional second derivative can be neglected when we go to really long channel device. So now without this term, so the thing becomes just the Poisson equation for one-dimensional MOS capacitor. Only modification is now electron does not follow just 0 quasi-Fermi potential depending on its position, channel-wise position. So it follows its own electron quasi-Fermi potential. So if we come back to our previous lecture material, so 10, so therefore I think that here. Okay, sorry about that. So our previous expression for electric field should be modified. However, the modification is quite limited. The only term related with the electron density is modified, and that is shown with a red color here. So now we are quite much ready to start our discussion. So if you review this kind of strategy, then you can find that looks good, but there is something missing. So we have not much talk about the equation, the second equation for electron transport. So we have spent quite much time for our Poisson equation, and also we made the specialization for one-dimensional this MOS capacitor. But what is the equation required for this electron transport? Which equation should be considered to describe the motion of electrons inside this system? Maybe you can say, if you are following my lecture correctly, then maybe you can say this one. Okay, electron movement just described by this simplified form. So yes, if we have this form, then that is corresponding to the current density. And let me just write down position wise. So if I ask you this simple question, how can you answer? Please try to write down your current density, electron current density, as a function of x and y position. Then of course you have to do this way, mu n. In principle, electron mobility can be a function of two-dimensional position, but in this modeling, so I'm not saying that this is really correct, but we will assume that this is a constant. So please note that it is treated as a constant. It is not a constant at all. Actually, this is very important to be being modeled. However, for a while, we will just assume that this is a constant. Then, what are remaining quantities? Yes, now we have electron density x comma y, and of course we have to have phi n. But fortunately, instead of this one, then now we can say dv over dy, and only y directional component survives. Then this one becomes just a simplified form of our current density at any position. So are you with me? This one is a more general form, but we have assumed that this electron quasi-Fermi potential is constant along vertical direction, x direction. So only y directional variation is allowed. So current is also flowing y direction. That is greatly simplified in this case. But more important thing I wanted to introduce today is it is not an equation. So this is not an equation. It is just saying that our current density is expressed in this way. This is just how can we express the current density, electron current density. Then what is, it's like this. Here we have a Poisson equation, and Poisson equation needs electron density. And if you remember correctly, in this case we introduce electron density is related with intrinsic carrier density exponential of something. So its role of this expression, Jn expression, is just like an expression for electron density. We need the equation for electron movement, so that is not covered yet. So today we will start from that equation. I mean that, yes, electron current density can be expressed in some specialized way, but that is just a supportive expression for our argument. In our discussion, we need the real equation, which is in the same level of the Poisson equation, and that answer is now shown. That is electron continuity equation. So now you have a whole set of two equations. Simply speaking, if you wanted to solve electrostatic problem, then you have to solve a Poisson equation. And if you wanted to know the movement of electrons or transport problem, then you have to consider electron continuity equation. Then what is actually this electron current continuity equation? So let me just explain. Continuity equation in general form just follows this way. So change of a certain quantity, so number of a certain particle really depends on this way. Divergence of flux of this one. This one is the form of our electron continuity equation. Or maybe you are not very happy with this newly introduced F sub n, but you have seen it before. When we consider electron current density, we also introduce flux, electron flux. Jn, that is having a unit of ampere per square centimeter, but you remember that flux, that is corresponding to number of particles per unit area at unit time period, so time duration. So this is the flux, and this was the current density. And if you remember correctly, they have the proportionality, so flux. And what was the proportional coefficient? That was minus q, because minus q is carried by our electrons. And if we go to, for example, a hole, then if we say hole, then the relation now becomes positive q, because positive q is carried by our holes. So you remember current density, the relation between current density and flux. And anyway, this is the electron continuity equation. And if I have to write down whole continuity equation, so I will just write down in this way, exactly same form, even in its sign. So simply speaking, here we have change of whole density at a certain position is corresponding to the minus times the divergence of our whole flux. Simply speaking, let me just explain. I assume that all of you already attended this vector calculus course. So this quantity, this divergence, means that if we consider a small volume, then this divergence simply gives us the net flux escaping from our small box. That is corresponding to this divergence. So number of particles escaping from the volume within a given or unit time interval, that is given as this divergence. So simply speaking, I'm saying that if within 1 minute, if 10 students leave this room, then we will have 10 less person in this room. That is specified by this simple rule. It means that, let's say that how can we remove a person or persons from this room? For example, if we are super persons, then maybe we can jump and demolish this building and escape. But we are not super persons, so the only way we can escape from this room is going to that axis and the door, open the door and escaping from that one. So electrons and holes cannot escape from this band structure immediately. So that's the reason why the only way they can escape from at a given position is their movement. So therefore, it simply means that if holes are escaping, then we will have less number of holes. So is it specific for holes? No, it is also specific, also applicable for electrons. If electrons are escaping, then we will have less electrons. Is it also applicable for human, the number of population? Yes, if persons are escaping from certain city or country, then the overall population of that city or that country will be reduced. Simply speaking, so we can write down the general form. Number of a certain thing is related with minus times of flux. So this is the general form of certain continuity equation. So why do we call it as electron continuity, hole continuity? The only difference is now we are concentrating on electron number or hole number. So therefore, we can consider also the population continuity equation, or all kind of different continuity equations can be made. But In this case, we are mainly concerned with this electron continuity equation because our interest is electron transport, not population variation in South Korea or worldwide. So now we have to consider this quantity. Then now you can see that. Please try to make it more accessible to all of us. Then how can you convert it to more accessible form or more familiar form? So please try to make it in terms of Jn. If we introduce Jn, so of course there is a certain conversion rule between current density and flux, and you can immediately find that they are cancelled out, negative signs, and now you will have a well-known form of our current electron current continuity. Following the same argument, we can see that whole continuity equation will just follow 1 over q divergence of Jp. So please note that in terms of flux, everything is quite much unified, even in their signs. However, since current density has the specific sign conventions for electrons and holes, that's the reason why when we write down those equations in terms of their own current densities, now we have a different signs. Don't be confused by this seemingly complicated sign conventions. So they have a well-established way to have these form. So anyway, now if you follow this argument, then now you understand I have to solve this equation everywhere. Everywhere means that at every position, every x position and every y position, the change of electron density should be balanced with divergence of current density. So let me just do it together with you. So in this case, please consider the specific form of our Jn. How does it look like? Jn just to look like in our specific example minus q mu n, which are regarded as a constant. Then now we have electron density x, y, and now dv over dy and y-axis. This is the specific form of our electron current density. Then please try to evaluate your divergence of Jn. Then how can you get the result of this operation? Of course, you have to once again x directional, y directional partial derivative, but well, in this case, what you have to do is this is just to y directional component, so you don't have to do actually x directional derivative. So y directional derivative should be partially derived with respect to only y. So it means that now you have to have a minus q mu n. Okay. Let me just erase some previous ones. Then now we have to have dy d n dv dy. That is required for our divergence. That becomes the divergence form of our simple expression. So simply speaking, I would say, let me just write down once again. So the one we have to do is n equal to q jn. However, since we have only y directional component, fortunately we can write down in this way: d round y and also j n y. So y directional component of Jn, that is the one we have to have in our continuity equation. So finally, I want to say, since we are considering steady state, values, physical quantities of our interest are just time independent. So now we can say that this one should vanish only because due to the steady state assumption, or simply speaking, DC assumption. We are now considering DC condition. So it means that this equation should be 0, and I think that this becomes too trivial, but as a result of a long discussion, now we can say that J and Y becomes a constant with respect to Y. We are not allowed any kind of variation in our current density. That is simple result. So if you cannot understand this one very well, then please try to this one. Here we have a certain resistor, and we have applied certain voltage difference, and we have R resistance. Then of course we will have a current I equal to V over R. Yes, everybody knows this one. And also we will have the same amount of current escaping from this lowly biased position. So you know that here we have a certain current, and here we have the same current. Then question is, somewhere here, what will be the current? And somewhere here, what will be the current? The answer is quite obvious. If we have certain highly conductive part or lowly conductive part, even inside a single resistor, it is not obeying what's called Ohm's law. Means that Ohm's law just states that if we have a certain voltage difference, then current, a certain given constant current is flowing through the entire resistor. So now we have to consider everywhere inside this system we have to have the same current. Quite similarly, we are considering MOSFET. The one we are considering is here y equal to 0 and y equal to L, and let's say that we have higher current and we have lower current. Then is it acceptable for our operation? Then what will happen? So more electrons are coming into this place and less electrons are escaping from this space. Then what will happen? The number of electrons will be increased and electrons will be accumulated. We will have time varying signal or time varying value of a number of electrons. But that is not allowed. Why? Because we have already assumed this DC conditions. Everything is just DC, steady state. We apply the time invariant voltage signal and expect that everything is just time invariant. So therefore this kind of net increase of electron density is not allowed. So in order to match this condition, then exactly same amount of electrons should escape. So that is corresponding to the continuity of our electron current density. So although we have spent quite a long time, but the answer is quite simple. Simply speaking, in our strategy, Jn should be a constant. It does not vary with respect to y direction. Every y position we have the same current. So that is the one we have. So let me just restate once again. Here we have an expression for current density. This is current density everywhere. It is shown here. Of course, this is corresponding to the gradient of our electron quasi-Fermi potential. And now, of course, think about this one. Here we have oxide, and now we have a certain V of y at this point, and another V of y at slightly different position. Of course, we can expect that it is slightly higher. Then, what we can say is there will be current. Also, there will be current. Also, there will be current. So let me just ask you one question. Here, we have the same amount of dV over dy. Then, where can you find the most conductive part inside this MOS system? Let's say that this is a gate and this is oxide, and here you have your semiconductor. Then, although dV over dy is identical for every vertical position, but you should be able to understand only nearby this interface we have a strong current, and if we go to slightly deeper into the substrate, we will have a much weaker drain current or electron current, and that will almost immediately vanishing when you go too deep into the substrate. Why? We share this form, dV over dy, but why we have vertical dependence of this current density? It is simply because we have also n dependence. Although they have the same driving force, but we don't have many electrons here. We don't have many electrons to carry the current. But instead of that, at the interface, we have tons of electrons, and they can move our charge quite efficiently. So, simply speaking, although this y-directional component are shared, but it just follows, the current density follows the depth profile of electron density. When electrons are many, then we can expect a strong electron conduction, and if we go to slightly deeper into the substrate, then almost no current conduction at all. So simply speaking, in order to calculate the current, please note that this is once again current density, ampere per square centimeter. In order to compare or convert it to the normal current, then we have to consider certain, how can I say, certain surface, certain area. Then how can we define certain area in this system? Its definition is quite obvious. I mean that if we have to consider certain area, then the area is given in this way. The area should be drawn in this way. So let me just use different color. We already assumed that there is the width of our transistor W, and also we have a x directional depth here. Of course, that is in principle that is infinitely deep, but you know, inside this deep substrate, nothing happens. We don't have electrons at all, so no current conduction is actually occurring. So current densities are only quite much localized nearby this nearby interface position. So simply speaking, if we have to define certain area for this current conduction, the thing we have to do is consider a certain two-dimensional space whose width is corresponding to the W and whose depth doesn't matter if it just covers the channel region. If inversion electrons are taken into account, then that is enough to perform this operation. Are you with me? It means that I just make it correct, so I wanted to extend it to in that way or that way. So please try to guess what will be the increase of current obtained by expanding this integration domain. So their net contribution will be just quite close to 0. Are you with me? So let's think about this one. So between two cities, let's assume there is a certain highway and cars are moving almost entirely through this highway. So if we wanted to correct the number of cars communicating between this city A and city B, then we have to, of course, consider certain toll gate and measure the number of cars passing through that point. But think about this one. I made this integration. I consider it in that way, but I wanted to do it more general and quite rigorous. So instead of that, I just extend it to in this way. Or consider much wide plane and try to measure number of cars passing through these positions, these areas. Then what will be the net contribution from this newly added area? You will find that they do not contribute at all because there is no load between these two cities, and although we are trying to measure additional quantities, so there is no contribution. Simply speaking, once again, between source and drain, we have a communication or movement of electrons, and in order to consider the number of electrons passing through a certain position, then passing through a certain y position, of course we have to consider certain area. However, if it covers most populated part here, then that is enough. You don't have to consider actually deep substrate because there is no hole, no electrons, and they do not move. So that is nothing related to our area consideration. So why I'm saying that way? So if we have to consider this drain current quantity, then we have to make two-dimensional integration. Then where can you find the two-dimensional integration in this equation? Then actually these are corresponding to the integration over two-dimensional surface. What is the meaning of this one? This W is corresponding to the G directional, width directional integration, and depth directional integration is required. However, here I'm saying that it is not expanded up to positive infinity. So it is just covered somewhere deep enough, far away from, just enoughly away from interface. That is enough to consider all kinds of electron contributions. Because if we expand it to infinity, then we will have a really negligible contribution for our electron density, and that does not contribute to our drain current. Okay, are you with me? So simply speaking, if we consider, let me just, I think that most of you already understand this one, but so let me just once again try to visualize this situation. So let's say that here we have a source and drain, and I mean that electrons are only moving through this top position, and there is a small amount of current conduction and almost nothing here. So therefore, although we have restricted our integration not entirely covering this depth scale, but if we just consider only a certain position, say xi, that is enough to consider all kinds of meaningful contribution for our current conduction. That is shown here. So limitation or upper limit of this integration should be considered in that way. So simply speaking, now we have a certain ampere scale quantity, the current itself, and that should be actually a constant. Although ID, this current, can be calculated at any arbitrary position, y equal to 0, y equal to L, half of L, or quarter of L, wherever we can try to calculate it. But if that is not a constant, if that really shows variation, then it means that we are now disobeying which equation? The electron continuity equation. So if that is not a constant of y, then we are now saying that we are disobeying the electron continuity equation. It is not allowed. Just like you cannot disobey the Poisson equation in this lecture, just similarly, you cannot disobey this electron continuity equation. So now the simple answer is, although that is in general a function of y, but that should be actually just ID or constant. So now that is our great simplification. Then if this ID is really a constant, then let me just do real simple one. Let's try to integrate this left hand side term and right side term from 0 to L. So sorry, I'm just doing really trivial one. So if that is the case, then I wanted to do ID dy from 0 to L. Also, I will do 0 to L integration of I dy dy. Then what will be the answer of this integration? Constant is integrated over the length scale L. Then you will have L times ID. That is really trivial. So we can say that ID, drain current, is simply given by 1 over L and integration of our seemingly position dependent quantity over the entire domain. This is nothing but just showing that constantness of this quantity. If this quantity is not a constant, then we do not have this equality. But no, due to the electron continuity equation, we know that ID is actually a constant, and we can do it in this way. Are you all with me? Then now the next topic is next step is quite obvious, because now we know the form of ID. Where can you find the form of ID? The form of ID is well shown here. Although it looks really complicated, but most of them are just constant. Q, constant. W, constant. And mobility is not a constant, but it is assumed as a constant. So they are all just coefficient, and only varying quantities are electron density and this dV over dy. But you know, there is no variation along x position, so this is just a function of y. So that really not simplifying, but gives us the real result for our calculation. Here ID now can be considered as this simple form. Simply say that, okay, so I have to cover this one. Okay, so let me just do it a little bit further. Electron density. Now it is done by mu n and phi over dx. So I'm just writing down the same thing. Yes, this is just copy and paste it, and now we have this form. And now here we have x directional integration. X directional integration, but please try to check our three different terms. Mu n. Do we have any dependence of mu n with respect to x position? Actually, we have, but that is assumed that a constant for y. So just forget about it. Then how about electron density? Yes, electron density itself has really strong position dependency. So we cannot kick out, we have to keep this quantity. Then how about dV over dy? dV over dy, from its construction, we already neglect its x directional dependency. So simply speaking, now I mean that although we have mu n and dV over dy and its vertical integration, I'm saying that these two can be pulled out from actual integration. Then let's just do that. Mu n dV over dy. Then the remaining one is nothing but just integration, vertical integration of electron density. Vertical integration of electron density is shown here. So let me just make an analogy. Here we have a classroom, and we have many tables and many chairs, and you are placed in a lattice point. Then it's like this. In the first row, how many students are there? In the second row, how many students are there? Third row, fourth row. If we add the number all together, then we can eventually calculate the number of students in this room. Quite similarly, here we have electron density function of nx comma y, and y is a given number, and we just make a slicing at a given x position. How many electrons? And differ in a deeper state, how many electrons? If we just make an integration all over this case, then we can get the total number of electrons. So sorry about that. So I will just explain once again. If this is electron density, and this is vertical position, and let's just say that electron density rapidly diminishing in this way. And what we are doing right now is just to consider a simple consideration. How many electrons are there? How many electrons are there? And this kind of x directional integration eventually gives us the total amount of electrons inside in this system. Please note that electron density itself is not just one-dimensional quantity. So what is the unit of this n? Do you remember? It is a unit of number of electrons per unit volume. So therefore, if we really perform this one-dimensional vertical integration, what we can get out of this integration will be, it is no longer number per cubic centimeter. So we will have number of electrons per what? square centimeter per unit area. How many electrons are found? That quantity is obtained by taking this vertical integration. Maybe you remember that I emphasized that you have to fill the numbers. For example, 10 to the 12 per per square centimeter. Is it high or low? 10 to the 10, 10 to the 13. I told you that this is moderate value, and 10 to the 13 is really high value for our electron density, and 10 to the 10 or lower, that should be regarded as a really negligible value for our electron density. Exactly, that quantity can be calculated by this integration. Integrating the volume density, three-dimensional density along vertical direction, depth direction. Now you will have the areal density of electrons, and this is the density of electrons seen from top of your transistor. From the top view, usually what we draw transistor, usually in this course we adopt this kind of coordinate system: x vertical direction, y, and of course here we have a z direction. But if we see it from the top of our transistor, then maybe we have a y-axis and z-axis. And where can you find the x-axis? So that is corresponding to your x-axis. This is a top view. So are you with me? This is vertical direction, and this vertical direction is hidden in this top view, and this is lateral direction, and now you are looking at this one, and this width direction is drawn here. This is top view, and in this case the quantity we just introduced, integration of electron density along the vertical direction simply means that how many electrons are found if we consider 1 centimeter and 1 centimeter. If we consider a small square whose size is 1 centimeter by 1 centimeter, then how many electrons are found within this small square? That is corresponding to this integration, and typical number is 10 to the 12 or 10 to the 13 for strong inversion case or moderate inversion case. So that is emphasized once again. So now you can understand. Here you have the vertical integration of a three-dimensional electron density, and it gives you areal electron density. So how many electrons per given area? If we multiply this minus q, the charge carried by one single electron, then eventually this entire term becomes nothing but qi, the charge due to our inversion electrons. So that's the reason why here we have q sub I. Here I is corresponding to the inversion. So in a simple way, simple meaning in this case, this is nothing but electron charge. Now we have this form. So let me just summarize. Here we have the form of current. This is current, not current density. Why? How did I get this current out of current density? By performing two-dimensional areal integration. And now, after some discussion, now we have this greatly simplified form. So total number of electrons or total charge due to electrons, and now we have dv over dy. This is the form of our ID. And of course here we have mu, w, they are all constant, so doesn't matter. So now we have this form. Then let me just plug in into our system. We know that drain current is now can be calculated from 1 over L and integration of our this position dependent quantity over entire channel domain. So let me just plug in here mu w dv over dy qi. So please wait for a while. So now this one is not important. This one is not important. But here we have two important parts. Here we have dv over dy qi, and you will immediately note that minus mu w, they are all constant, doesn't matter. But here combining this dv over dy and dy, eventually we can convert this integral into this integration for quasi-Fermi potential that can be combined into one, and here we have a qi. Of course, since the integration variable is now changed from y to v, of course we have to also change the integration range. Previously, when we change our y value from 0 to L, then what is the change of our quasi-Fermi potential? What is the quasi-Fermi potential at y equals 0? Source. It was source voltage. And what is the value of our quasi-Fermi potential at y equal L? I mean that drain. That is corresponding to drain voltage. So the answer is surprisingly simple. The integration now changed into the integration of charge with respect to the quasi-Fermi potential from source voltage to drain voltage. That is the result of our long discussion, and so now you can understand. Okay, so here, that is shown here, that is shown written here, and now we finally have this equation. Drain current is simply given as this 1 over L terms from integration, but most important one is this one. Nothing but by integrating our inversion charge density with respect to this electron quasi-Fermi potential from 0 to Vd. Why do we have this difference? Because this one is equal to Vd and this is equal to Vs. So now we have this really beautiful form. So if we can find the number of electrons as a function of electron quasi-Fermi potential, then now by integrating it over our electron quasi-Fermi potential, then that's it. So that is the result of this long discussion. Okay, are you with me? So are you happy? Okay, so looks really beautiful. Then the remaining question is, then if we can express Q sub I, inversion charge, as a function of electron quasi-Fermi potential, then we can calculate the ID. Then how can we understand the relation between Qi and V? So that is discussed here. So let me just do it. Although we have just 10 minutes, but let me just try to explain. So now you understand the importance of our discussion. So we have done quite well. So now if we can express Qi as a function of V, then we will have the complete understanding on drain current. But how can we do that? Let me just come back to the basic. So that by its definition, Qi is simply given as integration of vertical integration of electron density. And now here we have x directional integration, but that can be also converted into with variable transformation. Now we can say this one. Please have a look at this one. Yes, this is corresponding to really dx. Of course, once again, when you do this job, then we have to change their integration range. Position start from interface, go to a certain position far away from interface. Then please try to figure out the electrostatic potential at interface. So what is the electrostatic potential at the interface? That was defined as actually surface potential. So now we have surface potential. Then what is value of electrostatic potential at x equal somewhere inside our system, x equal to xi? Actually, we don't have a very definite definition about this xi. What is the actual value of xi? We don't care actually. If it is far away from 0, sufficiently larger than 0, then it's just okay. So since this is a little bit ambiguous, it means that we have also certain value. So simply speaking, this one should be regarded as electrostatic potential measured at x equal to xi. Point is, if we have different values for xi, then of course we will have different values for this delta, but that doesn't matter because already there is almost no electron at all, so their contribution to the electron density is really negligible. Once again, I spent quite a long time to explain somewhere here explain electrons are quite much concentrated on the area or part close to the interface, so we don't much care about the exact value of delta. If your integration really depends on delta, it means that your delta is not sufficiently large enough. So just to increase your delta a little bit, that is enough. Not increase it, but decrease it a little bit. It is approaching to 0. Sorry about that. So between this delta and phi s, which one is higher? Of course, this phi s is higher, and this delta is actually quite close to 0. It is small, but not 0 because our integration is limited up to xi. So now we are just playing with integration and changing the variable, but it is not just a tree. You can understand this quantity dx over dv. This is inverse of d phi over dx, and this quantity is corresponding to the x that is related with x directional electric field. Actually, it's a negative sign, so we will have this form. Yes. Now we have this quite much complicated form, but simply speaking, why do we have this strange electric field, inverse of x directional electric field, it is only because our original integration was x directional integration, but we made it to d phi integration. So as a result of this variable transformation, now we have this inverse of electric field. Therefore, finally, this is really finally, the expression for ID now looks like this. So here we have two integrals. One integral with respect to electron quasi-Fermi potential. And here we have integral over electrostatic potential. So therefore this one is called as a double integral. And it looks really complicated, but what does it mean is, although we have a double integral, please don't be overwhelmed by this complicated mathematical expression. You have to remember their origin. Why do we have this electrostatic potential integration? It was originated from x directional integration. And what is the origin of this dv integration? This is corresponding to our y directional integration. This expression, although looks so complicated, but it is nothing but just saying that our current density or our drain current can be obtained by this simple integration dx dy and jn, it's a y component x comma y. This is the origin of a seemingly complicated problem, and we just made variable transformation. Dx was converted into d phi over dx, and sorry about that, dx, d phi, and d phi. That is the way we convert it into d phi integration. And also in this case, we introduce dv and dv over dy. That is the way we convert it. Fortunately, this is quite a complicated term. This quite a complicated term is cancelled out by our Jn. Jn itself has dv over dy term, so they are cancelled out, so we don't have anything. And here we have something related to the vertical electric field, and we keep this vertical electric field term. So that is, I'm quite happy to cover our Pao-Sa double integral. Of course, it is named by the author of this paper, Pao. He was a PhD student, and Sa, he's a professor, mentioned here. He passed away in the last year. And anyway, this one provide us the complete understanding on MOSFET, long channel MOSFET's IV curve. Of course, if you ask me, is it really rigorous without any assumption, then we have to point out this one. It is within the gradual channel approximation. We have made the lateral variation of electric field is negligible compared to the vertical variation of vertical electric field. So that was, that was assumed. This one, that was assumed, and it was a gradual channel approximation. But if we go to the really long channel limit, that is really correct, and we can say that this is really corresponding to the real solution of our MOSFET. So then we have to think about this one. In general, if this system is, this modeling is not known to us, then the only way we can analyze this system is just to make a complicated computer program and consider every position x, y, and make a huge system, numerical system, and solve it. Then we will get a certain solution. That is actually many are doing in computer programming. But here you can see that by introducing a quite reasonable approximations, gradual channel approximation, and just to introduce effective mobility instead of position-dependent mobility, we were able to make a greatly simplified form of drain current, still valid at many cases. This is the power of modeling. Although we have brute force approach, can solve every problem by spending a lot of computing power, but if you are clever enough and diligent enough, then we can develop much more efficient way while keeping the physical soundness. So that is shown here. Okay, everybody love this one, but how can we actually evaluate this Pausa double integral? In order to really perform this one, think about this equation set. Q, yes, we know. Mu, we can set it. And W and L, they are designing parameters. We know them. Then, however, VDS, this is our applied drain voltage. So we can set 0 point something, 0. So this is set by ourselves. So Ni, intrinsic carrier density, that is known. And Na, that is doping density of our substrate, that is also known. Q, universal constant. Boltzmann constant, that is also universal constant. Temperature, that is our room temperature. We know the temperature. Then in this case, what is the real difficulty comes from? We can perform exponential quite well, but here we have Ex, electric field, at a given potential and given electron quadriform potential. What will be the vertical electric field? That is a little bit difficult and we need further elaboration. But most complicated part is not here. Please try to find out what is the hidden, the most difficult part to evaluate. You can see that because all of them are just covered, and now you can see that this one. The surface potential at a given y position or given electron quadriform potential, that really makes a problem. Once you can find this phi s at a given v value, then this integration becomes really trivial and you can do it. But how can you find the phi s? That is the real problem, and that will be covered in our next lecture, lecture 12. Okay. So it was exactly 60 years ago. It was a PhD thesis of Pao. Dr. Pao got his PhD with this work, and after 60 years later, we are currently living 2026, and we are studying it as a curriculum of just a senior level or junior level course. So therefore, don't be frustrated too much. So that is a very much a complicated one. So please do your best to study this one at your place. Okay, thank you.